We are going to do the lab. The lab normally is nice to do in person because this is where you actually are taking electrolytes or taking carbohydrates like sugar and putting them in water or in oil and see what happens. Putting in little electrical testers and see, does it complete a circuit or not? Unfortunately, we're gonna do this online. It's still gonna be kind of similar in that you are going to watch videos of me and Tina Christensen, who's one of the other physiology teachers, who, like when we had to go online, we went into the lab and we kind of did these and filmed ourselves doing them and did it in a way that you can still observe what is happening. And in your lab notebooks, you can still kind of write down your observations. So we're going to try to do this kind of in real time, as if you were doing the lab for real, meaning, I'm going to talk a little bit about exactly what you're seeing, and I'm also going to talk a little more about exactly what your lab notebook should look like, but I'm going to have you actually, recording in your lab book, like right now, like over the next hour and a half, you're going to be writing in your lab book, describing things that you're seeing on this video. So that's a cool looking cat. That's kind of like a tiger or something. A mix of a leopard and a tiger. I like the legs and that's nice.
Yeah, he's young, so he gets up in my business all the time.
Yeah, no, my dudes do that too. You'll see my cats before actually maybe not. They'll probably come up before this 2 weeks is up. So the lab is still going to give you what you need, and then we'll be getting into in-person labs soon. So we do have that going for us. And I'm just thinking, the pacing of everything is always weirder online than in person. And I think what we're going to probably, I think what we are going to do to keep things connected to what we've been talking about, we're going to start with part two, which is going to be like looking at electrolytes, and go to part 3, which is the carbohydrates. Part 2 and part 3 are related to each other intimately. Part 1 is kind of its own thing, looking at pH and buffers. And my worry is if we start with part 1, then we're going to run out of time in the middle of parts 2 and 3, which is going to be kind of wonky since they should be together. So I think we're going to start with the chemistry lab, part 2 and 3. And then assuming if we have time, we'll go into part 1. But if we don't, we'll continue with that on Tuesday. What you are going to need is you're going to need a lab notebook. Is there anybody who does not have their lab notebook yet?
I don't have mine yet.
Yeah, I haven't picked mine up either. I ordered it online and I have to pick it up this weekend.
All right, so if you do not have it, you still should be writing stuff down, because you're supposed to be writing things down like kind of as you see them. And what you can do is get a piece of paper. And you can write, like blah, 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 whatever, you basically can write single-sided as you're doing this and just hold on to them. And as soon as you get your lab notebook, these pages are oversized and you can just paste it in there. So even if you don't have it, the actual lab notebook, you'll be able to have your recordings of what we were doing today. And this is, you can do this if there's even in the next 4 months, if there's some day when for whatever reason you ended up in lab and you forgot your lab book, your lab notebook, you still need to make your observations like as you see them. So you just use the same method. You record things on a piece of paper, single-sided, which you can then just tape onto the pages, appropriate pages in your lab notebook. So if you either don't have your lab notebook right now, or Yasmin, like for you, it probably doesn't make sense until you know for sure you're in the class to like ruin a lab notebook, just write the observations single side, because you're going to have to tape it into the lab notebook.
Okay.
So if that makes sense. So just not having a lab notebook is fine right now. In general, you want to have it. Let's see. All right. You'll also need how many people don't have the lab manual? So a bunch of you don't have so if you go, so hopefully, has anybody, at least have you printed out the thing? Because I have it, I put it up on the Canvas. Is there anybody who does not have a printout of the lab for today?
I do. I'm not sure where to find it.
Oh, it's here, let's go share screen. So in general, let's see, we got this lecture week. Let me go down to the lab 1, chemistry review lab, just copy of lab manual pages. If you just click on there, there's going to be a PDF of the
Are you able to put that in the chat?
page. So it should come up. There it is. So you got it. So you do need so print this out. You're going to need this as well, because this is something you're going to be cutting these out and pasting them into your lab book to have the procedure. And also it's going to tell you what we're doing and how it goes. So to kind of do this lab today, you're going to need the lab notebook. You're going to need pens. You're going to need a printout of this thing. Hopefully, if you don't have your lab manual yet, you'll have that soon as well. So the lab notebook that you are going to be keeping, it is, like I mentioned last time, it's going to be worth a lot of your grade. It's going to be ultimately worth like 100 points, as much as one of the major exams. There are different parts of the lab. So like today's lab, this is like a demonstration lab. Meaning that there is not a formal objective and hypothesis and stuff. This is more just going to be, we've just been talking in lecture about polar versus non-polar and dissolving versus dissociating and all that. And this lab is going to be about, let's mix some stuff up and really demonstrate these concepts in a more physical way. The lab we're going to do next week, this jumping lab, is going to be a little different. There's going to be a question that we're going to try to answer. But for the demonstration labs, you still are going to need to have kind of the methods, like what you're actually doing, how you're doing it. This is going to be just from the lab manual. Cut and paste. like I mentioned last time, it seems silly for you to just transcribe everything if it's already typed already. So I made sure that we made the lab manual single-sided so you could just take the page and paste it in and done. For these multi-part labs, it probably makes sense, to do the cut out like we're going to start with part 2. So assuming you haven't already pasted anything in, you probably would have like the methods for part 2 that you're going to paste there. And then, your data is going to be record of your observations. So this is more raw. This is minimal interpretation. There might be a few, like I might ask some little questions in the lab manual that you might address or something. But in general, this is more just what you saw rather than the bigger thing of putting it into context and talking about what it all means and how it relates to the concepts in the course and la, la, la. So, for this lab today, it's going to be describing what you see when you try to mix the little crystals into the water, or what you hear when you put the electrical tester electrodes in and see if the circuit gets completed. So this is a record of your observations. And then there's going to be discussion conclusion. This is kind of this is kind of like the real meat of your lab write-up. This is where you talk about what does this data mean? What does it tell you? For today's class, it will be how does this relate to these deeper concepts we've just been talking about around dissolving, dissociating, hydrophobic, hydrophilic, the difference between polar and non-polar covalent, the difference between polar covalent and ionic in terms of particularly the behavior going into solution. So you can spend, today is going to be in Zoom, but when we're in person, you can spend 3 hours in lab and get the methods, do everything, get all the data, and still, not even get half credit on this lab. Because what's really important is, do you understand what does it all mean? Can you take this data and place it into the bigger context and show that you understand the kind of deeper ideas and how this data actually fits into the material that we're going over? So just putting that out there. The discussion is not just like an afterthought. It's not just like a sentence wrap up or something. It's where you really, it's not a term paper either, right? There's kind of a sweet spot between being a little too like, I don't know, short with it versus getting too crazy and going off the rails. And, I would say ask. If you are not sure what's appropriate, just ask, right? I mean, that's why I'm in office hours right after class, or you can email me, or you can send me a little example of what you've done and say, does this look about right? Or I am totally here to give you feedback. And so I don't want you to stress about but I don't know what I'm supposed to do. I'll work with you so you can know what's appropriate. But for today, you're going to be getting your data. And this, by the end of this hour, or it's another hour, no, actually, yeah, another hour and 10 minutes, you will have your data, at least for parts 2 and 3, written in your lab notebook. This part you'll be doing, kind of after. Sometimes there'll be time in lab to work on this, but this is often something that is after, lab will be a time to do the experiments, get the data, but then there's the next step with interpreting the data. What does it mean? How does it fit into things? Like I talked about in class last time, this class is not just the time you spend in class, it's also going to be time you spend outside of class. So don't let this slide too much. There are times when I have students, the cautionary tales, no names, but people who, they kind of get the main stuff and then they just never freaking get around to the most important part, which is interpreting it and discussing it and putting it into context. And by the time they finally do kind of look at it, they kind of forgot what the whole point of everything was. Or sometimes they don't even get to it at all, or they do it in a weird, confused way because they're, and there are people who have gone down grades or failed the class because their lab notebook was just never together. Not only that, the lab exams are open lab notebook. You actually get to have your lab notebook with you as you're taking the lab exam. So if your lab notebook is well done and discusses like what these things mean, it's like you're done, right? You kind of have the information that you need for the lab exam. It's kind of like this gift you gave to your future self back in the day when you were actually writing up the lab, right? Now, like 2 months later, it's like, wait, what was this lab about? Oh my God, I wrote it out here so nice and clearly. That's what it's about. So it's another reason to do well on this discussion or lab write-up is, one is you're getting graded on it, and two, it's also going to be your ally during the lab practicals because it is an open lab notebook lab practical.
So can we include things in the notebook that are helpful to us individually? Like if we put the metric conversion sheet that you sent us, is that something that, is that in our?
Yeah, so some things that are in your lab manual, anything in there would be appropriate.
Okay.
Like if there is some background information that's part of the lab that I wrote in there, that's totally appropriate. In fact, I would say you probably should put that in there because it's allowed. It's like, why not put it in there? The one thing I don't want your lab notebook to become is like a place where you put crib notes, like where we're talking about stuff and you just like put in all these crib notes about things that you think might be on an exam or something. That's not what it's supposed to be. It should be like a, if there's concepts that we talk about that are important to integrate, then it's important to, put them into the discussion. And they'll be in there, but you shouldn't have little factoids that are just randomly crammed in the margins because you think, oh, this is going to be helpful in my exam or something. It should be information that is about writing up the labs.
So do people ever have like a separate, like I take a lot of notes because that's how I listen and process. So do people have like a separate spiral where they might put their crib notes or like the random things they hear?
Absolutely. Yeah, sometimes it could be a separate thing. I mean, what I used to do when I took classes like this, I would just do a really clear demarcation of like, okay, I'm in lab mode. Here are notes in lab mode and back in lecture mode for a certain day. it's your style, but definitely, and in fact, what I would say is you would do well to do what Maggie is saying. Like when I am talking about the labs, particularly after we're done with the labs, I will be very explicit about what are the take-home messages here that I thought were important that you are going to want to include in your discussion. So if you've taken notes as we're kind of wrapping up the lab and I'm saying like, yeah, it's super important to realize like how these things both dissolved, but then they acted really differently in these other ways. Make sure that in your discussion, like you are very explicit about describing how they both dissolved, but then also acted in these very different ways and why that, what that tells us, right? So having some notes during the lab talking is going to be helpful for you.
Professor, question for you for the student in the wait list. It's going to be a little more difficult to find what all those things you asked for.
Right, so I would say, so for today, just do your best on this. By next week, I'll be able to let the waitlist people know whether or not they can be added or not, and at that point, you'll have full access to everything. So I would say.
So you just wanted to write something about demonstration about labs, let's say methods, date, and discussions of conclusions, stuff like that.
Yeah, wait, say that one more time.
All right. No, I said for right now, for today, you just wanted to write
Yeah, the data.
a
Yeah.
demonstration, right, from methods.
Yeah, so
And
the methods you'll tape in, and the data you're going to record from the videos we're going to watch right now. And the discussion conclusion stuff, that's something you can do once you know that you're in the class.
Oh, you're going to watch this, you're going to watch a move first.
Yeah, we're going to watch a video together in just a moment after I answer Carissa's question.
Oh, okay, I got you. All right. Thank you.
Carissa.
For the lab we are doing today, do we start with part 2 or do we leave a blank for part 1?
No, just start with part 2, because part 1 is not dependent upon parts 2 or 3 at all. So it doesn't have, yeah, it can just be, in fact, you could call it part 4 if you wanted. But yeah, just start with part 2. Here, I can like share screen here. You know, your page should basically start with this. It's going to be, here's this thing, and here's the procedure, which is going to describe what we're doing. And I can just describe it for you right here. You're going to use a spatula. You're going to add a little bit. We have 3 different electrolytes: sodium chloride, calcium chloride, and potassium chloride. You're going to put it in 3 little beakers. And then this is the kind of the description, the stuff you'll see on the screen. Describe the appearance of the electrolytes. So that would mean for each of these 3 things, describe what it looks like in the beaker. You know, spoiler alert, it's gonna be some kind of little white crystalline powder, right? But you actually want to describe it. You know, and then it says, then add 5 mils of distilled water to each beaker, swirl the contents, and record the appearance of each beaker again. So now you have 3 beakers where you've added water, and ultimately you're going to kind of see what happened. Did it dissolve or not? Did it disappear, go into solution? You know, then test each one with a continuity tester. This is, you'll see in the little video, this is basically a little buzzer circuit with these 2 wires. And if the thing conducts electricity, then it will complete the circuit and you'll hear a buzz. If it doesn't conduct electricity, you won't hear. This continuity means electrical continuity. It means that it conducts an electrical circuit. Hold on, let me roll up here. Then this part 2, choose one of the electrolytes, and you are going to try to dissolve that electrolyte into oil and see what happens. Does anyone have a guess what's going to happen if you try to dissolve an electrolyte into oil?
It won't dissolve
Why is that?
because it's not like dissolving like, it's like
Exactly.
dissolving unlike.
Exactly. If you're going to have a polar thing going in, oil is non-polar, you know, that's not going to have any charges for the for the electrolyte to play with. So if it's table salt, the sodiums and chlorines will just stay in their little crystal. There's nothing interesting going on in the oil. You're also going to test with an electrical continuity tester. What would you expect if you put salt into oil? Would you expect it to conduct electricity?
No,
No,
Why is that?
one's polar and one's non-polar.
And
Well, there's nothing to
it
disassociate.
hasn't.
It can't disassociate into ions.
yeah, so if it doesn't dissociate into ions, there's no charges floating around to actually be the electrical current, right? So, and also I know for some of you, these ideas are relatively new. So I'm kind of, it's hopefully having just heard it in lecture, doing this right now in person, it's all going to start kind of connecting and clicking. Part 3 of this is the exact same protocol, but instead of using electrolytes, we're going to use a carbohydrate. In particular, we're going to use sugar. We're going to add, so you'll add a little bit of glucose to the beaker and describe it. Add some water to the glucose and then describe what happens. Test the glucose, the sugar water with the electrical continuity tester and see what happens. And then these little questions here, these are like kind of small, but it was saying here, be sure your write-up for this lab has a discussion conclusion that summarizes, compares, and contrasts the results for testing the different kinds of compounds. So what you're going to do right now is do what I've just mentioned here and describe the kind of more immediate results. But then you're also going to, after we hang up on the Zoom call, spend a little bit of time going over what actually is going on there. So this is draw a ring form. I'll talk about this a little later. Okay, I'm going to mention one last little thing and then we're going to start here. So I talked about this idea of a solvent. In our case, it's almost always going to be water unless we're doing something special. The solute, the thing that you're dissolving in there. There are 3 different possibilities for what is going to happen when you take some solute and mix it up into the solvent. The stuff that we have been talking about up to this moment is what we call a true solution. So in a true solution, the solute dissolves and it never settles out. Basically, gravity might be pulling it down, but the attractions with the water and everything are pulling it up. Like if you have sugar water, you could leave that sugar water on the table and 3 weeks later, it's still sugar water. The sugar does not end up on the bottom of the cup. The other thing about a true solution is it does not scatter light. Which means it's kind of crystal clear. It might be colored, like you can have like glass that looks kind of red or green or blue, but it's glassy. So that is the true solution. That's like the most of what we're going to be looking at. That's what sugar water is, salt water is. Another one that actually is something that happens and that we're going to actually have to know for today's lab is a colloid. So here the solute dissolves and never settles. But these usually are where you have a much larger molecule that you're trying to get into solution, like starch. We'll talk about starch, which is these big chains of glucoses and stuff. It's hard to get it into solution in the first place. And once it's there, it stays in solution, but it scatters light. In general, it means it looks kind of milky. When you hold it up to the light, it doesn't look crystal clear. It looks kind of milky. Like in our lab today, there is part where you compare glucose solution to a starch solution. And the main difference you're going to see is the glucose solution, which is a true solution, just looks basically like water. And the solution of starch, which is actually a colloid, is going to look kind of foggy. I'll talk a little more about colloids later, but for right now, that's what you're going to see in today's lab. I should mention the last one here, call it suspension. In a suspension, the solute particles are big enough that eventually gravity pulls them down. If you've ever had like a thing of muddy water that looks just like muddy water, like brown water, but then you've got this kind of brown water, and then you let it sit for like a day or two, and then what do you see? It's like, oh my God, that's so crazy. It's actually just clear water with like a layer of mud on the bottom. Right? The mud eventually settles out to the bottom, the silt or whatever. If you shake it up, it'll look like the muddy water again, but then if you just give it some time, it will settle out again. Your blood is a suspension. Normally the blood cells are suspended in the plasma, but if the blood just sits there in a jar, all the cells eventually end up as a big clump on the bottom. When we do some of our blood labs, we're going to spin the blood in a centrifuge and speed up the process and pull all the blood cells down to the bottom of the tube. Go on.
Sorry, so in a suspension, the solute particles don't dissolve?
Yeah, so I mean, they can be like kind of hanging out in a kind of more homogeneous like mixture for a while, but eventually they will end up at the bottom. So they don't dissolve in the way that you saw a like a true solution or something where things are, but they dissolve in that they are kind of interspersed in there. They're not all just immediately like just separating like oil and water or something. A lot of medicines are prepared as a suspension. If you have some medicine in a little jar and or a little bottle and it says, suspension of blah, 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 what do you have to do before you actually give your patient this medicine?
Shake it up.
You got to shake it up. Because if it's just been sitting on the shelf, probably all the good stuff is down at the bottom of the jar. So you got to shake it up to bring it back up and make a more homogeneous mixture.
It's because the half-life is around 4 hours, 2 hours. That's why.
Say it again.
Then I say the reason you have to shake it up is because the half-life, it's short. It's around 1 hour, 2 hours.
Half-life is another different concept. We're going to talk about half-life. I'm not sure. There's different things. half-life is not what I would normally think here and as more appropriate to think about as suspension. We'll talk about half-lives. I'm not exactly sure how you're using it in this context. All right. So let's dig in.
Can I ask a question about cutting the methods and pasting them in?
For sure.
Are you saying just cut right out of our lab manual? And so for an example on this one, is it pretty much just like the bottom half of page 17, part 2?
Yeah, exactly.
Okay. And then there's, the next page, there's the top half of the page. But do we want to just kind of cut out the, the real important stuff and paste it in?
Yeah, I would, like we were talking, because you have the ability to put everything in there, why not? Why not put everything in there? I'm trying to show some of, like this is a jumping lab, but just kind of showing for Enzyme Activity Lab here, right? He cut out the instructions here. So you can do it like that. Here, this lab.
This is
so you can just kind of cut and paste and tape them in there.
And then do we write our
Hey,
own?
Professor.
I'm sorry. So who is first here? That's right. Question?
I said, do we need to write in every lab, do we write our own objective?
So for the demonstration labs, you don't need to have an objective. The
Okay.
objective is basically demonstrate the concepts.
Got it.
The labs where you need a specific objective and hypothesis, those are kind of highlighted in the schedule. So like the jumping lab will need one, but not for this one. Another question, comment?
Yeah, Professor, could you leave the questions from the first page, just to be looked at?
I'm having trouble understanding you.
No, the lab, the questions, can you just leave it there on the page 1, just to be take a photo? Just to be start the material. What are you asking?
I think he's asking you just to show the PDF of the thing so he can take a photo of the screen.
Thank you.
Sure. Let's see. Here, this is from Rebecca. Actually, do I have it in?
Yeah, the pages are in the chat, Marcos. Can you see
Marcos,
them?
Rebecca.
Because I don't have the. If I cannot access to the computer, it doesn't have the computer.
I was. We're gonna run out of time here. I'm gonna continue, just get the lab going. I would say you can follow along and just leave space for the lab instructions, and you'll be able to put them in. But I'm worried that we are going to not have time even to finish parts 1 and 2 if we don't actually just get into this here. So I'm gonna keep rolling along. Rolling. Okay. Right, and you'll see what to write down, and it'll still make sense even if you don't have it printed out right now. Hopefully. Okay. Doo-doo-doo. All right, and actually, I'm going to publish this as well. So that way, if you want to go back to any of this, you will have access to it. So bing, it now has all of a sudden magically appeared in your Canvas portal in this Lab 1 module here. Again, so part 1, we're going to do later. We're going to do part 2 right now. So, it says like for each of these, so here, record the data and observations in your lab notebook as if you were personally doing it, but do be clear that you're not actually doing it. You don't ever want your lab to be kind of a piece of fiction of like, oh yes, I did this. It's like, this isn't like, you have to say like, these are my observations from watching the video. That is important. Like there are people sometimes who like to do this kind of dry lab thing, never actually do the lab and write down what they think they're supposed to see and didn't actually ever do it themselves. That's not okay. This is supposed to be kind of a true and honest representation of your experience. And one the other thing I should mention while you're doing this, and this or any kind of lab, this idea of a sanity check. As you are doing these labs, as you're recording your data or your observations or doing calculations, if you ever get some answer or something that doesn't make sense, slow down and figure out what might have gone wrong. The sanity check means, does this make sense in the real world at all? Or am I going crazy? Right? It's like you do some measurement and you weigh a canary and it comes out to 365 pounds. It's like, okay, something went wrong here. There's no way a canary weighs 365 pounds. That doesn't make sense, right? You measure somebody's height and you decide that they are, 56 centimeters tall, which is like, about 2 feet. It's like, okay, no, they're not a leprechaun. Something went wrong here. You mix sugar into water and you end up getting a crazy oil slick. This happens when we do this lab in real person. People will add some sugar or salt to water and describe, what do you see? Oh, it's like, when you dissolve sugar in water, you get these crazy oil slicks. It's like, wait, does that make sense? You've spent like your whole life putting sugar in water, and have you ever seen an oil slick show up? What's probably happening? And what's probably happening there?
Contamination.
Yeah, contamination.
Yeah.
It probably like whoever had this beaker last did not wash it very well. So as you're doing these experiments, you do want to record your data, and sometimes it's not going to be what you expect, but at the same time, remember this idea of sanity check. If you're going to do some calculation or you're doing something or other, do a quick little check. Does this make sense? It can really save you a lot of grief doing these quick little approximation things to see if you're in the ballpark of with anything. All right, so here we go.
Can I ask one final question? I'm so sorry. So I have like everything cut out and ready to go. So just the first section we're supposed to be doing right now is just the observation while we watch this, and just basically writing down what we're seeing and that we are watching a video.
Correct.
Okay, great.
And this is beginning on page 3 of our manual. And
Absolutely.
the table of contents with the experiments, don't necessarily have to be in order, just according to the date, right?
Yeah, so I mean, it's whatever experiment you're doing, that will be the next line and then the page that it's on. So it's going to be, and we might end up shifting some experiments, or maybe not doing some experiments or adding in experiments. So don't write your table of contents as this whole big thing that's pre-made. It's going to appear line by line over the weeks as we do experiments.
But so we're supposed to start on page 3, not on page 2?
No, because page 2 is like the back of the table of contents. That's kind of awkward. And
Oh,
what
I
if-
didn't, I thought we weren't supposed to skip pages. Okay, I'll start on page 3.
Yeah, the
Thank you.
table of contents might go. Yeah, so I would say in general, you are correct. In general, you don't want to skip pages. But in this, yeah, in this case, it makes sense.
Can you
And
tell that people have a certain amount of anxiety about writing in this lab notebook?
I'm very
In
scared.
10.
all right,
So
so
we're starting right now with observations in pen and our lab notebook, right?
correct.
Okay.
And I think I talk a little bit about even how you record data and stuff. We'll see. So here you get to see me at the beginning of the pandemic. This is not the most flattering like screen here, but whatever. Ah! All right. All right, Kim. So again, this is all available for you now. It's just in that module. So if you want to look at this again, you can. It's easy. And I am basically, I'm going to play it. Probably pause it for places where you need to write things down. But in general, this is kind of what you would have been doing if you had been in lab. All right, so now we're going to do 2 and 3 of the chemistry review lab. And parts 2 and 3 are very similar to each other. It's just part 2 is dealing with electrolytes, and part 3 is going to do the same basic steps, but with carbohydrate, in this case, glucose. And just to kind of give you a sense of kind of this mechanics of putting the lab book together. Here we have data down from the last part of the lab, probably leave a little space to kind of write up, but then we're gonna just have the instructions for part 2 here for electrolytes. Yeah, I'm doing this quick. In reality, you would do this a little more thought out. But basically, I have the instructions for the lab right here. So, and you can use a glue stick is better than tape. And then I'm just going to follow. It's really important when you're doing the labs to follow it step by step. And we'll be reviewing, here are the broad overview of how the lab goes. But even if you think you know what you're doing, you still got to slow down and read step by step because there's often subtleties. And also often we're taking the data from many different groups and we're averaging it all together. And you can't do that responsibly unless every group did the experiment in the exact same way. So it's really important, as much as you're gung-ho to just get data, to actually slow down, have at least like one person in your group who is the official kind of reader, gonna get more pedantic and yeah. So I'm gonna say part 1, use a spatula to add small equal amounts, a large pinch of the dry electrolytes, sodium chloride, potassium chloride, and calcium chloride to 3 separate 50 ml beakers. So these are the little 50 ml beakers here. They're very cute. And we're gonna put a pinch. A pinch is basically what it sounds like. There's a picture in your lab book showing a little bit. It should be enough that you can actually see it, but not so much that it's not going to dissolve in a little bit of water if it wants to dissolve. Come over here, and I've got each of these spatulas is labeled so I don't cross-contaminate between the different things. And I also probably want to make sure I mark what these are. So I'm gonna use a pencil here and I'm gonna have some potassium chloride, calcium chloride, sodium chloride. So that's another thing. In a lot of these labs, you're gonna have very similar looking tubes or beakers, but with different stuff. And it's another place where you want to get kind of pedantic and be good about your record keeping and marking what's what so you don't get confused about things. So here, potassium chloride and a pinch, again, enough that you can see like the end of your fingernail, but not too much because otherwise it's, you know, if you try to dissolve a whole cup of sugar in a teacup or something, that's it's ridiculous. So I'm gonna put all of these in and then our camera will come and look at this a little more closely. I've got calcium chloride, again, a little pinch. And I'm gonna put that in that one. Get my sodium chloride here, and we're gonna now all right. So I'm gonna take these and put them like with a black background where I think it's gonna be easier to see. And in each case, hopefully you'll be able to see there's this kind of these little white crystals. Right. So this is kind of this first stop, right? This is this observation, just what is this electrolyte? These are 3 different electrolytes, right? You have calcium chloride here. We have, which one? This is a sodium chloride, potassium chloride. They are just sitting here as their little crystals. You know, the ions are holding onto each other in a crystal lattice. And you know, this shouldn't be surprising. If you looked at this thing like sodium chloride, which you know is table salt, and it looked like totally bizarre, you know, again, that's kind of that sanity check. It better look kind of like table salt. You've got a lot of experience in your life of table salt. So
Sufficient to describe it as looks like table salt, or do you want it specific, large crystal clusters, or?
yeah, I mean, I'd say like, yes, kind of small whitish crystals would be a good, you know, and then you could use like table salt as well, but because that is a bit more of a subjective thing, based on your impression of table salt, I would say using something more generic, like, you know, small white crystals is probably appropriate. But yeah, you can see they all look pretty similar. Right, and again, we had to make sure we have enough to actually see it, and that way we can see if it dissolves or not. We have to make sure to see if it disappears. So that means we have to see if it's there in the first place. But if you have too much, you can supersaturate. There's a maximum amount of stuff that can dissolve, even if it does dissolve, at which point, you know, things won't go into solution.
So the beaker on the left is the calcium chloride. Can you go over which ones are which again, really quick?
Yeah, at the base of each of them. So there's, again, right here, we have the sodium chloride, which is just ordinary table salt. This one is potassium chloride. This one is the calcium chloride. Hopefully you'll be able to see there's this kind of, right, which is heck. Trying to get dagnabbit. So I'm going to take these and put them like with a black background where I think it's going to be easier to see. And in each case, hopefully you'll be able to see there's this kind of these little white crystals at the base. Yeah, so sodium chloride is far right, calcium chloride far left, potassium chloride's the electrolyte in the middle.
Quick question, sorry to go back, but what did you paste underneath the the part 2 electrolytes? Was that the data results called discussion and conclusion? There was two things that you taped to the first page.
Oh, it was on two pages. So it's like, there was a page break. Like, so
Right. So it's, oh, maybe not. What am I missing?
It's like part 1, A, B, and C.
yeah, well, part two, A.
Sorry, yeah, part 2, like A. Oh well, bullet point 1. Part, A is on one page, but B and C are on the next page.
Okay, I can't find it, but all right.
Sarah,
I'll
I
figure
sent you a picture.
Okay, thank you.
It was part 2 methods was across 2 pages. So I had to like cut half of one page and half of another page to get the whole thing. All right, so this shouldn't take too long to just, but you want to make sure also in your lab notebook, you are writing those, like this is part, la 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 la. Oh, wait a second.
A.
Wait, so now I'm missing. So whatever, is this part, it's part 2A, is it? Yeah, so just make sure you say what these observations are related to in the methods, right? So that's what I was saying. So make sure like it's not just some random white crystals. It's like, what, according to what is this part of? What is this supposed to be for? So now we're going to continue on. The next part is it says you add in the water and see what happens. We're going to do that. Base of each of them. Again, right here, we have the sodium chloride, which is just ordinary table salt. This one is potassium chloride. This one is the calcium chloride. And this is where you're writing things in your lab book. When it says, describe the appearance of the dry electrolytes, you actually want to record that in your lab notebook. Use your pen and write down the words that describe, granular, white, fluffy, whatever words. And this is kind of a qualitative description here. So, there's no right answer other than it should reflect what your observation is. And it needs to be something that you record while you're actually experiencing it. Memory is pretty imperfect. You don't want to go back and think, oh yeah, I think it was on a white powder later on. That's not what your lab notebook is about. That's not what science is about. Empirical data is what you observe. So you need to record while you are observing it. So I guess the important thing about taking data is that you record what you actually see. Sometimes it's not what you expect, and that's still okay. You write it down. It's true and honest record of your work, not like kind of what you would have seen in an ideal world or what you expect your teacher to write down. So now it says after I've actually, I would write down again like KCl. I'll look at it. It's white fine grains. Etc. I'm not going to spend all the time doing it right now, but you would if you were here. And then I'm going to add water. It says add 5 mils of distilled water to each beaker, and then swirl the contents. To measure out the distilled water, I'm going to use a pipette. These pipettes are for much more accurate volume measurements. And you always want to use one of these little pipetter attachments here, which basically sucks up. You don't want to ever use your mouth-to-mouth pipette because you might get something inside you don't want. These are a little confusing for people at first to understand. They come in different volumes. This one here is a 5 mil pipette, and it's designed to dispense volumes up to 5 milliliters. And the way it works is you would put it in the liquid you're trying to pipette. And the numbers actually kind of go upside down. They start at 4 at the bottom, and the 3 to 2 to 1 and 0 is up here. So the technique you would use is you actually suck up until you are at the 0. And that means now there is 5 mils in the pipette. And when I squirt water out, so this is just water, so this is actually safe. If I do that, this goes down to the 1. That means I have just dispensed 1 mil. I've now dispensed 2 mils and I'm down to the 2. I've now dispensed 3 mils, I'm down to a 3. I got it all out, I have just dispensed all 5 mils. So because I need 5 mils inside each of these, I can just pull up to the 0. Yeah, I'll just say, we'll be using these a lot over the semester. So yeah, just remembering that they work by sucking all the way up to the 0, which means 0 has left the pipette. And then you squirt out and it will tell you how many mils have left the pipette that way. So it's a pretty, it works well. I'm gonna quickly. 5 mils there. Suck up again, up to the 0. 5 mils there. Suck up to the 0. So here we've got all of our electrolytes. And again, electrolytes, you should know what it means to be an electrolyte. And what do potassium chloride, sodium chloride, calcium chloride all have in common? And I just mixed them with water. And now kind of take a look. So if you take a look, do you see any crystals in there anymore? I think I've got a picture going over the top as well. No. And here we're trying to decide, you know, I should warn you. So this looks like maybe there's something in there, but any little spot, I should have cleaned the table better before we did this. Any little spot that's still on the table can appear as if it's actually in the thing if it's under the glass. So I can say, having actually been there personally when we made this video, these all look just like clear water. Record the appearance, like, can you see it still? Did it dissolve? So this is what it looked like when you added water to any of those 3 electrolytes. So you want to make sure you put that in your description now. Kind of, I mean, again, it shouldn't be a surprise. You should all have a pretty solid expectation for what happens if you add a little bit of salt or sugar to salt to water.
Do you need to write a description for each one, or can you clump them together if they're the same? Like I wrote, after adding 5 milliliters of water to each beaker, the electrolytes dissolved and solutions are clear.
Yeah, that would be appropriate. And that's one way to do it. You know, another way that you could have been doing it is to have like a table where, like, I should have mentioned this probably a little earlier, but a classic thing to do if you're doing the same thing to many things, you do some kind of chart, like, you know, compound, you know, appearance, dry, appearance, wet. So there's different ways to do it. There's no, like I mentioned last time as class, there's no one right way to do a lab notebook write-up. Well, although there are wrong ways, like if you didn't record the data, or you recorded it wrong, or you made it up what you thought you should have seen, that's not right. But there's lots of correct ways to do it. So yeah, what you said sounds fine. Doing it as a chart like I wrote would be fine. And lots of other possibilities too. So then we're going to continue on. The next part is the idea of the electrical continuity tester, to see how each of these responds to an electrical current trying to pass through it. And here we go.
Oh, disappeared. I have to say, looking at these, they all pretty much look like they've dissolved. I don't really see the granules in there anymore.
You can't see the video.
Can't see the screen.
Yeah.
He's going to be testing.
Thank you. All right.
For electrical continuity, basically whether or not it can conduct electricity. And conducting electricity is basically, an electric current is moving charge. So for there to be an electric current, there has to be charge moving, in the wires, in the lighting in the room, it's electrons moving through the wires. In most biological systems, when you have electricity, the electric current is ions that are moving. So having ions, independent ions floating around in a solution typically is going to allow an electric current to flow. We can test that. I have this nifty little thing set up here. It's actually just a power supply, a little buzzer. This thing is a little buzzer, and wires that if I connect these two wires together, it completes the circuit, and you should be able to hear the buzzer. So wires are separate, no electrical current flowing from one wire to the other. I don't hear anything. I have the two copper wires touching. I hear it. So this is just a really simple way to see if something conducts electricity well. The air right now is not conducting electricity very well because I don't hear a buzzer there's no electric current flowing through the air from wire to wire when they're separated. I can take one of these solutions, and again, these wires are not touching, but if I put the solution flooding, so both wires are underneath and submerged by the solution, I can see if I hear the buzzer going. And when you do this, you want to make sure that the wires have a lot of surface area in contact with the solution. If you just like barely dip their noses down, there's so little contact, you're not really going to get a good answer. But here, I'm going to take these. I'm going to put them in. This right here is the calcium chloride. Let's see what happens. All right, so on the air, I don't hear anything. In calcium chloride, I hear a buzz.
Right, so that's going to be something you're going to record. And those wires were not touching; they were just underwater in the calcium chloride solution, and obviously the electrical current was able to travel, which you could hear through the. All right, so that was calcium chloride, and we're going to continue on and look at the other two.
I can rinse these little guys off with some distilled water. I want to make sure I'm not kind of cross-contaminating stuff. It's not, normally I would just have like a little beer. So I'm cleaning these off. Now I'm going to go into my sodium chloride. I get the same thing. Air, they don't, there's no electrical current. I'm going to put them, submerge them in the sodium chloride. I don't know if you can hear that. I definitely you can hear the little buzz go. And then we can look for the continuity. You know, we put the wires, but they do not want to, they don't make a current in the air, but if they are submerged under the potassium chloride, I can hear a buzz. So again, parallel, so they're not touching. Want to make sure that there's a large surface area submerged, and sure enough. So that is that. The last part is.
All right, so there we've kind of got the electrical continuity. What did we see? What can we say about the electrical continuity of electrolyte solutions?
That they all have an electrical current.
Yeah, so obviously something more than just dissolving happened. Obviously the crystals disappeared and dissolved, but something deeper is going on too, because all of a sudden now this solution has the ability to conduct electricity, which we're going to be able to compare and contrast when we actually go and do the same thing with the sugar in a few moments. But the next thing we're going to do before we leave the electrolytes, we're going to try to do the same thing, but instead of dissolving them in water, we're going to dissolve them in oil. Does anybody have a sense of what you're going to see if you try to dissolve this electrolyte in oil?
No buzzing.
No buzzing, and even more.
They won't even dissolve.
Yeah, so let's watch. Let's watch what happens here.
It says pick any of those electrolytes, and now instead of dissolving them in water, put them in oil. So let's do that. And I'm going to take one of my little beakers. And it doesn't matter which electrolyte I pick, I'll pick salt because it's the one that table salt is the one I'm most familiar with in my life. Take some. Again, take a pinch. I add it to my beaker. I don't need to label this because it's only one electrolyte. So this is the salt. If you take a look at it, it looks like salt. And now I'm going to take the mineral oil, and I can take 5 mils of mineral oil. Same basic way. Suck up to the 0. And I have 5 mils in my tube, and then dispense. That's going to be 5 mils of oil that are now in my beaker. And now I kind of mix it up. And I don't know if you can tell, if you can see the crystals. I don't see the crystals dissolving. I just see.
Right. Again, it's a little tricky with the reflections. Can you see that the salt crystals are just still sitting there in the oil? So this is important. This is something.
See a bunch of
oh, you silly goose.
Crystals lying in the oil.
There, that's a pretty good view of it. So you want to, so this is now putting salt, but trying to dissolve it in a non-polar solvent, which is oil. And this, write down in your lab book what you see here. Later on in your discussion, you're going to be able to be more elaborate about what it means and why this is different from the water. But for right now, you just have the raw data. Right. And then the last part is going to be trying the electrical continuity tester on this. So I'll just kind of run that and let it happen.
There. if it's possible. Does that show up there? And then I can check continuity, with the electrical continuity. And I take my wires and I'm holding them parallel so they're not touching. And I'm going to submerge them in this mineral oil salt solution. And make sure they're fully submerged. And now I don't hear anything. Right? Air, no buzz. Oil and sodium chloride, no buzz. Now, again, you can double check, fail safe, make sure the system's actually working. If I touch the wires, I totally hear a buzz. So the system is working. It's just I did not have electric current when I was just testing my solution. And that's more data I'd be recording in my lab notebook.
Which you should record in your lab notebook. So there we have another piece of information that you're going to be able to integrate into your discussion. Yeah, so we're almost done with this.
I have a quick question.
Sure.
Even though they don't dissolve, are they still considered solutions since they're together?
So it would be more like a mixture, right?
Okay.
And it's like you've got a solute and a solvent, but you're trying to mix them up, but it's not becoming a true solution because it's not actually going in that way.
Can I also ask, which electrolyte did you choose? I know it was just once. Which one did he use?
That was sodium chloride.
Okay, great.
As table salt. So for the last part here, we're going to do the same thing, but with sugar, glucose. So let's look at that, and then that'll actually get us just to the end here. So we'll wrap it up with that, and we'll have to do part 1 next week. So here we're going to go.
And a little later on, I'll be spending more time kind of interpreting what does it all mean. But the first step is while you're actually getting the data is just to keep an accurate record of your observations. All right, so now we're on part 3 of the chemistry review lab, which is basically the same thing as part 2, except instead of using an electrolyte, we're using a carbohydrate, in this case, glucose. So I'm gonna get my little 50 ml beaker and I'm gonna put a pinch of glucose in it. And I go find the glucose. I find the appropriate labeled glucose spatula. And pinch of glucose. There's my pinch of glucose, my beaker, put it in. And again, you can kind of take a look and see there's a little granulated glucose crystals in there, which again, you would record
back. All right, so you can see it looks awfully like, all the rest of them, they all look like little white grains. What is different? What is holding the atoms together in a glucose molecule?
Covalent bonds.
Covalent bonds. Yeah, so it's very different, not ionic bonds. This is covalent bonded. And what subtype of covalent bonds?
Hydrogen bonds.
No, that's a different kind of bond.
Okay.
Polar?
Polar, it's polar covalent bonds. I was mentioning having the little hydroxyls hanging off the ring, having the oxygen in the ring. There's lots of places where you're going to have local charge imbalances in this glucose molecule, where one part or another part will be a little more positive or a little more negative. So this is a classic example of a polar covalently bonded molecule. What do we expect is going to happen if we put a polar covalent compound in water?
It'll dissolve.
But
Right.
not dissociate.
Yeah. So dissolve, it's going to dissolve, but it's not going to break apart and dissociate like the electrolyte. So it's going to be similar and different. So let's watch. So again, you can write down, oh, look, it's another white crystal.
Record in your lab notebook. Then you're gonna pull up 5 mils of distilled water. Gonna add the 5 mils of distilled water. Agitate, give it a chance to dissolve if it's gonna dissolve. And you can take a look. And it's worth, you know, especially if you still have your other beakers out. Like I have a beaker of sodium chloride here. You know, they both look pretty much the same. You know, what does dissolve mean? The crystals have gone into solution. But then we're gonna look at it.
Right, so I guess observation, it dissolved. The crystals disappeared, and whatever those molecules were before in a crystal, they're now dancing with the water molecules. Oh. Then we can try the conductive, electrical conductivity.
Another thing, so here we've looked at, does it dissolve or not, which we did with the electrolytes. We can now look at the electrical continuity. Again, double checking. Yep, system is online. I'm gonna hold my little wires parallel so they're not touching. And now I'm gonna fully submerge them under this sugar water. And I don't hear anything. So that's telling me something about the electrical conduction of sugar water. And again, if you remember, if we were looking at the sodium chloride, again, it looks physically exactly the same. But if I put the wires in there, very different response. So like in your discussion, you know, parts 2 and part 3, even though they're kind of separate parts, in your discussion, you should probably kind of integrate your observations for both the electrolytes and carbohydrates under the same conditions, and how they are similar and how they're different and why that makes sense. The last part of the carbohydrate part is just.
All right, so did everybody hear what I said there? Like, you've got your observations for parts 2 and 3. The discussion will be more integrated. You know, these two parts are actually, actually parts of one larger thing. So in your discussion, make sure you talk about what these observations are and how it relates to all these concepts we've been talking about, and why, how things are similar and different, and why. The last 30 seconds I have here is just showing you the sugar versus the starch water. So I'll just do this for completeness.
Just looking at the optical difference of what sugar water glucose solution looks like compared to starch solution. It's starch, which is just a whole bunch of glucoses bonded together in big long chains. But when they go, and it will go into solution, but it becomes a complex. It's worth taking a look here. And this is the sugar water, a true solution, which by definition is not going to scatter light, is going to basically be transparent. Whereas when you have a starch solution, I don't know if you can kind of notice it here, a colloid does scatter light, which basically. So it's hard to see a little bit, but hopefully you can see that this thing on the left is kind of foggier or milkier looking. That's a classic sign that you've got a colloid. The colloid, it's dissolved. The starch is in solution. It won't settle out, but it looks kind of milky. That's what we mean by scattering light. Whereas the sugar water, this is kind of a dirty bottle, but the sugar water is just completely clear. So means it's kind of cloudy or milky looking. And hopefully that part of, this is a demonstration lab, trying to get you to just have a more personal sense of like, oh yeah, I see that glucose dissolves into a transparent solution, whereas the starch is dissolving but it's creating a different kind of mixture, this colloid, which you can physically see as being different. So.
All right, so
Question, isn't sugar a starch? Or sugar's the carbohydrate?
starch, we're going to talk about in much more detail. So carbohydrate includes sugar and starch. Starch is just made up of a bunch of sugar subunits connected together in long chains.
Okay, so it's a long chain and a short chain is what was being compared in those two bottles?
Yeah, so glucose is not even a chain. Glucose is like the single unit, and starch is like a big polymer made out of a whole bunch of glucoses connected together.
Thank you.
So they're both, one's called a polysaccharide, one's called a monosaccharide. And they're both polar. It's just the starch molecule is much bigger and does not, does not go in clear. So any questions about any of this stuff?
Are we going to be responsible for doing part 1 on our own, or we're going to pick that up next week?
No, we're going to pick that up next week. Again, these first 2 weeks are, obviously got kind of thrown slightly off balance compared to how we were originally going to run this all. So, I'm kind of doing my best to do it so you get the material and also don't feel like lost. So I want to make sure like we can start off the semester where you actually feel like you actually know what we're up to, rather than like trying to desperately catch up on something and get all confused. That being said, I would spend some time this weekend writing up your initial discussion on this first part. Again, it doesn't have to be like a dissertation. It just might be a page or something, but it has to really talk about your observations and how they relate to each other and how they relate to the concepts we've been talking about, and how they illustrate what we've been talking about. So, and I say do it while these ideas are fresh and this kind of experiment is fresh in your mind, because that way you don't have to go back and try to like go, what are we doing there? What's going on? What's this mean? So you take way less time doing this stuff when it's fresh than if you go back later and have to like try to recreate like what the heck you were up to in the first place, then like go to the next step. So next week we will continue. I'll try to figure out exactly how to adjust the jumping lab as well. But assume we are going to finish this lab and that we'll be starting the jumping lab at least next week. And then hopefully the week after that, we'll be back in class. Yeah, next week will still be a lot of chem review. We still have to we haven't talked about different kinds of reactions or metabolic pathways or ways of specifying concentration, or just the details of carbohydrates versus proteins versus lipids and stuff like that, which we do need to go into detail, at least to some degree. So lots more chem review to come. I also, there will be a small warm-up quiz that is going to show up before Tuesday. And those before each class, I didn't have one for today because we didn't really cover much anything last class. But normally I have these little quizzes that are only worth a point. They're really not worth anything in terms of your overall grade. They're more just to kind of keep you caught up and give me information as well that people are keeping up. So there'll be like a very short, literally 1 point quiz. Each subpart of the questions will be worth anything from like 1 point down to like 1/4 of a point, or so, not 1 point. Either 0.2 points is the highest point of a question, and sometimes the questions are worth less. So it's really not about points. It's about just checking in. Are you keeping up and giving you and me feedback on how things are going? So don't be surprised if warm-up quiz number 1 appears on your radar sometime in the next couple of days. Anyway, that's it. If you have questions about anything, I will be here for the next hour or so. Otherwise, have a good weekend.